Okay, so I think it's time to start. So today's lecture will be devoted to Riemannian. We will discuss Riemannian manifolds. And in particular, we will start with some, so probably we will touch on some, one of the models of the hyperbolic space, mainly the upper half plane model of H2. Also, we probably, if time permits, we will probably discuss Lie groups and symmetric spaces. So I will put it in parentheses, and Lie groups plus symmetric spaces. Okay, so first of all, let M be a smooth manifold. And from now on, most of our manifolds are assumed to be smooth, okay? So this means that we have an atlas of charts, right? Basically, charts are homeomorphisms. So we have a manifold M, and our charts are open sets U. Here, this definition allows actually to define smooth maps between manifolds. So the definition F from manifold M to N is smooth if it is so in charts. If it is smooth in charts. So looking at the picture, we have actually manifolds here. Let me basically just draw a diagram. So we have M to N, right? We have also maps phi sub U to the phi U of U sitting in R. I don't know. Okay, I started with M being an N manifold, but okay, so let it be Rn. Here we also have some chart psi V, and its image is already sitting in Rk, suppose the dimension is K. And so we have something here and something here. We can pass to this map, which is F, I don't know, tilde, right? So if F tilde for every pair of charts here and here, it is this F tilde is smooth, then our map, our continuous map F from M to N is also said to be smooth. As a special case, we can define smooth curves. Okay, so a smooth curve is just a smooth map. It's a smooth map gamma from some interval in R1 to M, right? Okay, one can define the velocity vector gamma prime of t. And in fact, we can define this tangent space. So another definition is that the tangent space I will denote it as TPM, is the set of equivalence classes. So it is the set of equivalence classes of velocity vectors. I will write the vector V equals gamma prime of 0, right? The derivative where gamma is a smooth curve. I will just write it this way. And gamma of 0 is P. So this is a smooth curve passing through the point P. Okay, so this is the set of equivalence classes. This phrasing has a little bit, well, has several interpretations. One can think of just vectors having the same velocity at this point 0, okay? Or you can think of like that it doesn't really change with the respect to change of basis. So this definition is actually, well, this is a well-defined object, meaning that it doesn't depend on your charts, since if you pass from one chart to another, you will multiply just basically by the Jacobian matrix, okay? So the tangent space, why this space is particularly interesting, since first of all, a few facts about that. The dimension of the tangent space is also M as a dimension of the manifold M, sorry, N. I started with N. So this TPM is basically generated by the vectors whom I will denote just by E1 and so on, En. Sometimes they are denoted as partial derivatives, but this is just the notation. In fact, what is important for us is that the dual space TPM star is generated by differentials along the coordinates. So if we have the idea is that if we have a vector, sorry, if we have a point P, right, it sits in some chart. Thus, we have a homeo to an area in Rn. And then we have there x1 and so on xn. We just take the images of coordinate lines there to we then map it to the chart, and thus we get the and then we take their velocity vectors. This gives us the basis in the tangent space at the point P. The idea is that the tangent space, we kind of abstractly think it's like it touches our manifold, but again, this is actually a pretty abstract object. Sometimes you do not have anything sitting anywhere, but geometrically you can imagine that this behaves like that. Okay, so this is my cotangent space or dual space, and this is my tangent space. Now I'm going to define I'm going to define a Riemannian metric. Yes, and the idea is that these behave like that. So dxi applied to ej, it is a linear function, so it is equal to the Kronecker symbol, which is 1, well, which is 0 if I is not equal to j, and 1 if I equals j, okay? But we will use it a bit later. So a Riemannian metric now a Riemannian metric on M, it is the positive definite. There's a positive definite, well, I will write symmetric, but it is not needed since it's already positive definite, symmetric, bilinear form, or I can say a smooth, right, smooth tensor to field which I can write in the following way. So this is G. It is usually denoted by G. I will write sigma for now, but usually it's omitted in the special tensor notation. So Gij, it depends on the coordinates x. And here I have dxi tensor product dxj, right? Sometimes in differential geometry, people use the upper indices, and then they omit the notation with sigma, assuming that if the indices repeat in lower and upper case, then you need to take the sum, right? Okay, we will not like be using this Riemannian and differential geometry notations quite a lot, so I'm not lazy. I'm not so lazy to write it down. For now, it's okay. Okay, so how can one think of this? It is basically just it is kind of a symmetric bilinear form living in the tangent bundle. So we have our manifolds, right? We have a point P. We think that there is a tangent space, right? TPM. And in each TPM, we have a positive definite symmetric matrix. So the matrix, which I will denote as G, right? It is the matrix Gij X and Gij equals G Ji, and this matrix is positive definite, meaning that the quadratic form associated to this matrix is positive definite, is a positive definite quadratic form. So one can think of the matrix that sits in each tangent space here. The entries of this matrix smoothly depend on the coordinates, right, on the local coordinates of our manifolds, and in every tangent space, the matrix is symmetric and positive definite. Okay, so an example is definitely one can take any. Okay, it can be Rn, right, with the standard Euclidean metric, which I will denote by Ge. So this is Ge. It is dx1, standard product dx1, plus and so on dxn. And for simplicity, we will just use dx1 squared plus and so on dxn squared. This means that the matrix of our metric in every tangent space is just the diagonal identity matrix, okay? And yeah, so in fact, one can take, say, U2. I will denote it as U2, that this is an upper half plane. It is a pair of points in R2 such that y is greater or equal than 0. And of course, U2 can be also equipped with this Euclidean metric here. It's not a big deal. Right, and I didn't write it down, but a Riemannian manifold is a pair. So a Riemannian manifold is a pair M and G, where G is a Riemannian metric. On M. And the third example, take any submanifold, any submanifold in Rn and restrict G, the Euclidean metric, on the tangent bundle of Tm. As a special case of this example, one can take a sphere, a two-dimensional sphere in R3, and if you want to make it like properly, you should take the tangent space here, and then you will just physically, so you will write, say, in spherical coordinates, you can choose spherical coordinates, write down the point, and then your sphere is given in these coordinates, right, by some kind of equations. You can differentiate them, and you will really write your vectors. So the idea is that your vectors will be vectors of length 3, right, since they sit in R3, but they will be parameterized in with respect to parameters, u and v. Yeah. So, okay, in fact, since we know that actually any smooth manifold can be embedded in a higher dimensional Euclidean manifold, then any smooth manifold can be equipped with some Euclidean metric. But the point is that one can choose different metrics. And already quite soon we will discuss another metric on the upper half plane. But before that, I wanted to discuss the geodesics and isometries. Okay, so an isometry, the term we'll be using quite a lot during this semester, during this course. An isometry is actually, so let me define it in a more general version. So let M, G, and N H be Riemannian manifolds. The two Riemannian manifolds. Then F from M to N is an isometry if F is a diffeomorphism, right? Is a diffeomorphism, and the image of, so we have two vectors here, U and V. We have one manifold, right? Then the map goes to, this is F of M, and it is known that if we have a point Q, which is F of P, right? The map which sends the tangent space to the tangent space is the differential, right? It is, so this notation df is not just the notation, it's actually a nice map that sends, it's a linear map that sends tangent space to tangent space. So we want these metrics to agree with each other with respect to this map F, which means that G of U and V equals H of df of U and df of V, and we want it to work at any, so this is, I will write with index P, here I will write it with index F of P, and this should work for any P, right, in M, and the pair of vectors in the tangent space TPM, right? Since it is a diffeomorphism, I can just then write it in the actually for the reverse isometry or the reverse So in particular, it implies that there is that F inverse is also is an isometry, right? Okay. Now we will mainly consider isometries, which are kind of like self-isometries. So the isometries of the map, of a manifold M to itself. But okay, right now I would like to define. I think I would like to define geodesics, and then yes, generally why Riemannian metrics are interesting for us. It's so one can use to do some like geometric computations on manifolds. So in particular, like how can we use metrics? Okay, so for example, if you want to compute an angle between two tangent vectors, right, you can use the formula that the cosine of angle between two vectors is the following ratio. It is the scalar product of these two vectors with respect to this metric over the product of norms, product GP dV, where GP U times U is basically just the norm of the vector U squared, right? Okay, one can also compute the length of curves, and in fact, one can compute volumes and so on, but let me just write it down for the length. So length of curves. We will just use the standard formula for the length of a curve in Rn, but we will modify it with respect to the fact that now we are not in the Euclidean metric, but we are in some metric. And the length, I will usually denote it as follows. I will write L of gamma restricted on T belonging to some segment AB. And usually this T belongs to the segment I will omit, and I will just write down the segment itself. So this is the integral from A to B. Okay, let me move it a little bit to the right. So the integral from A to B. And here I'm writing basically the norm of the velocity vector of gamma, right? So gamma is a map from some interval to M, T to gamma of T. And here I'm writing the norm, but I'm already choosing this instead of just writing the norm. So this is going to look like that. It is going to be G, but computed in which point, right? Since it is our curve, and now the point changes, right? So this is gamma of A, this is gamma of B, and here, generally, it is some gamma of T, right? So I'm writing G gamma of T and gamma prime of T, gamma prime of T, the square of it, and with respect to the parameter T. So this is the length of curve. And geodesics are those that locally realize the distance between points. What does it mean? It means that I can define the distance, right? I can define the standard, the metric, the word metric in the standard sense. So the distance rho of between points P and Q, by definition, is the infimum Okay, let me write it down by this. So it is infimum of L of gamma on 0, 1, such that gamma is it belongs to G smooth from some subset of R and M, such that okay, I will just write the I, right? Such that gamma of 0 is P, gamma of 1 is Q, right? So I'm taking the infimum of length of curves connecting to points P and Q, right? And I'm taking this infimum by all such smooth curves. And if if a curve gamma locally realizes the distance, it is called a geodesic. What does it mean it locally realizes? It means that, so we have points P and Q, right? It is like this segment PQ is an image of gamma of the segment 0 and 1. So this is my, right, segment. Then for every point T here, I want to have some interval T1, T2, right? So my gamma of T is some point here. This is my gamma of T1, T2. So I'm writing this way. For every T in 0, 1, right, there exists T1 and T2. So the interval T1, T2 containing T, such that the distance rho between gamma of T1 and gamma of T2 precisely equals the length of our curve gamma on restricted on the segment T1, T2. So if this happens, then gamma is called a geodesic. In fact, one can reparameterize any curve to have a natural, the so-called natural parameterization, such that the velocity vector has constant norm. And if you did this, if you reparameterized your curve in such a way, then this condition can be rewritten in the way that this length is just equal to the difference between T1 and between T2 and T1, right? Basically, the absolute value of the difference. But do not confuse it with the main condition, right? This can be done for any curve, for any smooth curve. What is important is that the distance between the points on the manifold is equal, right, to the length. So it's indeed, so there exists a geodesic that locally realizes the distance. The condition locally is important. Your geodesic may be locally geodesic, but globally it's not necessary. And a good example is a sphere. So let me move it down. Sorry, move it up and this more down. And here I'm going to probably before making this remark, I want to note another fact which we are going to use quite a lot. So important proposition. If F is an isometry then the image of a geodesic is another, well, maybe the same geodesic, but it's the important fact is that it is also a geodesic, right? So, not, of course, I do not mean here the same. So, this can be checked directly from the, it is really straightforward because of the definition of this isometry, right? It preserves an isometry, and actually Riemannian isometries are very nice. Okay, now some, again, probably some examples. So in R, say in R2, right? Straight lines. Geodesics are straight lines. It is a famous fact, but you can just use it, you can prove it by your own. One way to prove it is to write down the length of a curve explicitly, to do some computations, and indeed to see that only straight lines minimize the distance between 2 points. A little bit more clever way is to move any pair to show that isometries in the Euclidean space are translations, reflections, rotations. So isometries are the following classes of elements. So translations, reflections, rotations, and actually you can generate any isometry by some amount of reflections, or you can use translations plus reflections. But in any case, you can take pair of points P and Q and move P to 0. So there exists an F, which is from the isometry group of the R2, right? There exists F such that F of P is 0 and F of Q is some point on the on the axis X, okay? And then it is a little bit more simple to write down the integral and to see that indeed only this segment minimizes the distance. So we will see that the straight lines are geodesics. On S2, isometry group is actually quite simple. Isometry group of the sphere S2 is the orthogonal group, of order 3, which is denoted by O3R. And one can show that geodesics are great circles. Geodesics are so-called great circles. To get them, one need to take the section. So if one have 2 points, say P and Q, one need to take the plane, which is generated by those 3 points, P, Q, and the origin, the center of the sphere. And then this gives you a central section of the sphere, and this gives you the geodesic. This line itself is a straight line in the sense of Riemannian metric on the sphere. And the point is that you have 2 geodesics, actually, 2 geodesic arcs containing P and Q on the sphere, right? And usually one is shorter and another one is longer. But locally, both arcs are geodesics. But if you take P and Q, the opposite points, you will actually have infinitely many geodesics having the same length passing through these 2 points, right? So geodesics can be, generally speaking, they can be not uniquely determined. And also this was about the global versus local realizing the distance, right? So this example partially illustrates this fact that locally and globally is not the same. One more remark. Generally speaking, Riemannian manifolds may have quite, like I would say, quite poor isometry groups. There are very weird examples, as I guess there are probably no isometries, or there are only finitely many, or so generally it is not like the isometry group is not really, it doesn't always help you that much. Okay, but in our case, we will deal with manifolds having very good isometry groups. In particular, we will always have an isometry that sends one point to any other point. So this means that isometry group acts transitively on our manifold M. And this allows in particular to describe geodesics, since you know that, moreover, in this sense, our manifolds are the so-called homogeneous, meaning that the neighborhood of any point in the space is isometric to the like kind of the same neighborhood of another point in the space. Okay, now I want to finally describe one model of the hyperbolic plane, and this will be the upper half plane model. Okay, so upper half plane model of H2. So U2 is the set of pairs xy from R2 such that y is greater or equal than 0. Then we take the hyperbolic metric HU, which I will write as follows. It is dx squared plus dy squared, but divided by y squared. So it is a Euclidean metric, but with some like scaling factor here. And this changes the geometry actually pretty much. So one can also identify this with this like complex, I would say like complex interpretation. One can take the complex numbers z such that the imaginary part, how is it usually denoted? I guess something like that, right?
Usually right, I am. Maybe one y strictly greater than 0. So
Strictly greater than, yeah, yes, indeed. Yeah, this is a good point. Yeah, I want to take the open subset of R2. So this is strictly greater than 0. Yeah, but we choose another metric. And it is like the well-known fact that the group of conformal automorphisms of U2, or sometimes it is also denoted as, it is actually isometric. So conformal automorphisms in the sense of complex analysis. It is isometric to the group of Möbius transformations on U2, which consists of maps Z to AZ plus B over CZ plus D, such that A, B, C, D guys are real, and AD minus BC is okay. It is non-zero. Usually it's taken to be non-zero, but in fact, since the scaling like all ABCD simultaneously doesn't change the image, right? One can write that it is actually equal to 1, right? This group is interesting since to any such map, right, one can assign a matrix A, B, C, D, and this matrix, so this is just the matrix such that AD minus BC is equal to 1, right? So this is from 2 times 2 matrices such that the determinant is equal to 1. There is the special notation for this group. It is the so-called special linear group. But this map, large phi, it will have a kernel. And its kernel is going to be plus minus identity. So there is a very nice map, right, between this and this groups. And in fact, it turns out that the automorphism group, yeah. So in fact, this gives us the isomorphism. So this implies, right, I will say that this implies that this out of U2 is isomorphic to PSL to R. And this PSL to R is precisely the quotient by this kernel. Okay, this is very nice. And now I'm going to remark that, but what are the like typical, I would say typical classical elements or elementary, some elementary transformations sitting in this? We have actually the following types, right? So elementary Möbius or fractional linear transformations. So elementary guys are translations in the Euclidean sense, which send z to z plus, alpha, where alpha is real, right? Okay. Yeah, I hope I will have time to say a few words about geodesics, and then we will stop. So translations, rotations around points, so they look like that. We have, okay, what is this simplest case? I think I will just write it in general. Okay, this is rotation with respect to some angle theta, z, if we rotate around the origin. But if we rotate around some other point, say beta, then it will be minus beta plus beta, I guess, right? And also I want to introduce dilations and inversions. Dilations or Euclidean homotheties are just z to lambda z, where lambda again is real, and actually it is positive number. It is a positive number. And the last one is inversions. Z to 1 over, I think it should be 1 over z bar. Or no, it is just 1 over z. And the point is that this inversion, it is a composition. So it is a composition. It is a composition of a Euclidean reflection which is z to z bar, the conjugate, which is a reflection with respect to the real axis, and a Euclidean inversion with respect to the unit circle, and an inversion with respect to the unit circle. So geometrically, it looks like making an inversion looks like that. You take the point, so x goes to, sorry, it's better to denote by, so z goes to some z prime, such that the product of lengths of these two segments, right, oz times oz prime is equal to the square of the circle here, which is basically 1. And in fact, this means that the norm of z times the norms of z prime is equal to 1, right? But in the sense of those transformations, this is not like an inversion, but it is a composition of an inversion with respect to a circle plus reflection. Okay, why I wrote this down? Since you can show that any transformation is a composition of these 4 types, well, it can be quite long, but you can decompose into the product of elementary transformations, and you can show that, so this follows, right? First of all, you can notice that every guy is here, and the corollary, let me write it down, so the corollary, that the automorphism of U2 is a subgroup of isometries of the manifold U2 with this geometric GU, right?
Describe will send the upper half plane, lower half plane, and also the thing that you described as negative determinant. I think you want negative 1 over z. So you add also a rotation to switch points.
Okay, let me think. Wait, I goes to, okay, say the point I.
I will go to negative.
Yes, 1 over I is negative I. Okay, so probably, or with the conjugation, no? Probably I should add probably the bar, right?
So the conjugation will not be conformal.
Yes, yes, it will not be conformal.
So
Yes, probably I need this. But let's just double check. Yeah, I know how to check this. We can look just at the matrix, right?
matrix is sort of
Yeah,
object 0, 1, 0.
yeah, 0 or 0 minus 1, 1, 0. Right. We want the determinant to be equal to 1. Yeah, thanks. Indeed. So this should be z to minus 1 over z. Or more generally, you can write down -1 over z minus some number, right? If you want to make it to be inversion with respect to a shifted circle. But anyways, it is a composition, right? So you can decompose any Möbius transformation in some probably quite a long sequence of those elementary guys, and then you prove the following fact. And this is very important, that these guys are, it is the subgroup of an isometry group of this upper half plane. You can show that just step by step for every elementary guy that this transformation is an isometry. So all these are isometries. Isometries. This is the first part, and then you, as a consequence, it is an isometry group. And then another corollary, I'm basically, I'm already running out of time, but let me fix it. I want to write it down here. So another important fact is that what are geodesics in this model? And this is the theorem. Geodesics in the model U2 with the metric GU are either the vertical lines or, so the vertical lines orthogonal to the boundary, or the circles orthogonal to the boundary, meaning the, so it is not the entire circle, but this is a circle arc such that the center belongs to the boundary, right? So these are two types of geodesics. And two types of geodesics in U2, but I really need to specify what is the metric, right? Since in U2 with the Euclidean metric, only straight lines, but in any direction will be geodesics. Another interesting fact is that actually this group PSL2R, which is the automorphism group of the U2, and which is isomorphic to PSL2R, it acts definitely transitively. In fact, this should have been mentioned first, transitively, on U2, and any triple, and on triples of order points, and on triples ordered, okay, just I will write ordered triples of points, ordered triples of points in the compactified, in the U2 bar, which is not just U2, but it is also U2 with the axis imaginary part of z equals 0, and plus the infinite points. So we also add the infinite point. So this is my boundary, infinite point, and all the points here, right? And in particular, this means that any 3 points on the boundary can be mapped to any other 3 points on the boundary. And you can show this fact about geodesics by just mapping the half circle, the semicircle to the vertical line, and then again use kind of an elementary integral considerations to show that a vertical axis passing through the points is a geodesic. But we'll probably do it on Thursday. Okay, thank you. Thanks for your attention. If you have questions, please ask or write down by mail.